Hello my friends, and welcome back to the Today Machine channel.
The Neeland shipbuilding press is a versatile system designed for creating complex, double-curved hull panels in shipbuilding. One of its key applications is the cold forming of saddle-shaped panels, commonly known as side stretch panels, due to their characteristic elongated longitudinal sides. To form a saddle panel, the process typically begins with bending tools mounted on the SBP. These tools create a cylindrical base shape, providing the foundational curvature required for the panel. After achieving the initial bend, the operator switches to rolling tools, either by using a pre-configured press or by mounting the rolling unit on the same press. This tool change is streamlined, requiring approximately 20 minutes if performed manually. Alternatively, a press with the rolling unit already installed eliminates this step. The rolling process involves the PWU rolling unit, consisting of upper and lower wheels rotating in opposite directions. This stage is critical for elongating the panel's longitudinal edges, transforming the cylindrical form into a saddle shape. Rolling is highly effective for creating complex geometries while maintaining a smooth surface finish and strengthening the metal without compromising its integrity. Operators use the intuitive interface to precisely control the process, ensuring the panel matches predefined templates. The shipbuilding press's ability to combine bending, rolling, and stamping in one system makes it uniquely efficient for shipbuilding applications. Its modular design supports quick tool changes, enabling seamless transitions between forming stages. The press's range of capabilities, from 2,750 kilonewtons to 15,000 kilonewtons force, accommodates various panel sizes and thicknesses, making it suitable for diverse shipbuilding requirements. The final step involves spot stretching or additional bending to fine-tune the saddle panel's shape, ensuring it aligns with design specifications. By integrating these processes into one system, the shipbuilding press enhances productivity and precision in producing double-curved panels, such as saddle shapes, critical to modern ship hull designs. This innovation represents a significant leap in efficiency and accuracy in the shipbuilding industry. Hot forming is a specialized manufacturing process employed to shape thick materials, like the 125 mm thick Hemi head. At Wada, this process demonstrates advanced engineering capabilities and robust infrastructure to handle heavy-duty tasks. Process begins with the selection of high-grade raw materials, often austenitic or ferritic steels, known for their excellent heat and deformation characteristics. The material is preheated to a carefully controlled temperature, typically exceeding 900 degrees Celsius, within high-capacity furnaces to ensure uniform thermal distribution across the entire thickness. Once the material achieves the desired temperature, it is transferred to the forming press. Here, state-of-the-art hydraulic presses exert immense force, ensuring the material is shaped accurately into the Hemi head profile. The thickness of 125 mm presents a unique challenge, requiring precision in pressure application and consistent deformation to prevent surface cracks or internal defects. Post-forming, the component undergoes controlled cooling, often by air or water spray, to refine its microstructure. This step enhances the mechanical properties, such as strength and ductility, critical for applications in industries like oil and gas, power generation, and chemical processing. The workshop adheres to stringent quality standards, incorporating non-destructive testing methods like ultrasonic testing and dimensional inspections to verify the component's integrity and compliance with customer specifications. At Walter Tosto in Chieti, Italy, a stainless steel plate for the ITER vacuum vessel undergoes a precise hot forming process, showcasing cutting-edge engineering. Part of the AMW consortium, with Ansaldo Nuclear and Mangiarotti, this facility uses an open die technique to shape the metal. Heated to extreme temperatures, the plate becomes pliable, allowing it to be pressed into the exact form needed for the vacuum vessel, a critical component of the ITER fusion reactor. This vessel will house the plasma where nuclear fusion occurs, requiring unparalleled precision and durability. Walter Tosto's expertise ensures the component meets stringent quality standards, contributing to ITER's ambitious goal of advancing sustainable energy through fusion technology. The process exemplifies the fusion of craftsmanship and innovation vital for this groundbreaking project. The fabrication process for each sector involves 4 segments: the inboard, upper, equatorial, and lower. Inboard segment, PS1, involves electron beam, E-beam, welding on FSH, IWS rib welding, and outer shell welding. Upper segment, PS2, includes inner shell welding, esh-hole machining, and intermodular key welding, followed by PAUT testing and final machining. Equatorial segment, PS3, requires FSH modeling, machining, rib welding, IWS block installation, and outer shell fabrication. Each sector is a massive structure, weighing 440 tons and standing over 14 meters tall. Once assembled, the vacuum vessel will span 19.4 meters in diameter, 11.4 meters in height, and weigh approximately 5,200 tons, increasing to 8,500 tons after in-vessel components such as the blanket and diverter are installed. Lower segment, PS4, focuses on shell machining, turnover, and E-beam welding. After individual segment production, the sectors are assembled through rigorous fit-up, splice plate installation, and helium leak testing. The integration of more than 1.6 kilometers of welding per sector highlights the complexity of the process. South Korea's fourth and final sector was delivered to the ITER construction site in Cadarache, France, after a global voyage. Hyundai Heavy Industries, supported by the Korea Institute of Fusion Energy, has delivered on its commitments while also contributing superconductors, thermal shields, and assembly tools to ITER. The vacuum vessel's double-walled structure incorporates in-wall shielding blocks made from braided and ferromagnetic stainless steel to protect components and enhance plasma performance. Approximately 9,000 blocks, 2/3 pre-installed, occupy 55% of the vessel's interstitial space. ITER cryostat assembly is a monumental engineering challenge, often described as the world's largest puzzle. ITER, the International Thermonuclear Experimental Reactor, aims to demonstrate the scientific and technical feasibility of fusion power. At 30 meters in diameter and height, the ITER tokamak will house a vast array of intricate subsystems and components, demanding extreme precision and coordination. The assembly process takes place primarily in the tokamak building, embedded within a concrete bioshield to maintain a controlled environment. The building operates as a clean area with strict temperature regulation to prevent dimensional changes in the massive components. Adjacent to it, the assembly hall handles pre-assembly of major subsystems. The cryostat, the largest single component of ITER, forms the heart of this operation. Its assembly begins with the placement of the lower feeders for the magnetic systems, followed by the cryostat base, which weighs a staggering 1,200 tons. Subsequent steps include installing thermal shields, gravity supports for toroidal field coils, and the smaller poloidal field coil number 6. The cryostat's lower cylinder, thermal shielding, and central support structures are carefully added in a bottom-up sequence. Subassembly preparation happens concurrently in the assembly hall. Here, each of the 940 degrees vacuum vessel sectors, their thermal shields, and 2 poloidal field coils are precisely pre-assembled. Specialized tools, including subassembly rigs and heavy lifting cranes, manage the maneuvering of these oversized components. A sophisticated system of twin-bridge cranes spans 175 meters, equipped with 4 375-ton hoists capable of handling up to 1,500 tons. The final assembly in the tokamak building involves aligning and welding the 9 sectors into a cohesive structure. Precision optical metrology ensures tolerances as tight as 2 to 3 millimeters, crucial for the machine's functionality. Over 161 custom tools, with capacities ranging from 500 to 1,500 tons, facilitate these tasks. China's flange forging industry is one of the largest globally, driven by its extensive steel production and robust demand in sectors like oil and gas, petrochemicals, shipbuilding, and construction. In 2023, China produced approximately 30% of the world's forged flanges, with an estimated output exceeding 1.2 million tons annually. The market size was valued at around $5.5 billion, growing at a compound annual growth rate of 5.7%. The industry benefits from China's abundant raw material supply, competitive labor costs, and advanced manufacturing capabilities. Major production hubs include Jiangsu, Zhejiang, and Shandong provinces, which collectively account for over 60% of the country's flange production. These regions are home to state-of-the-art forging facilities capable of producing a wide range of flanges, including slip-on, blind, weld neck, threaded, and custom designs, catering to both domestic and international markets. China has over 300 registered manufacturers specializing in flange forging, with a significant portion meeting international standards. Many of these manufacturers export to Europe, the United States, and Southeast Asia, with exports constituting nearly 40% of total production. In 2022, flange exports from China amounted to $2 billion, making it a key player in the global market. Technological advancements in the industry include the adoption of automated forging lines, precision CNC machining, and real-time quality control systems. These innovations have improved efficiency, reduced lead times, and enhanced product quality, solidifying China's competitive edge. However, the industry faces challenges such as increasing environmental regulations and fluctuating raw material prices, which push manufacturers toward sustainable practices and cost optimization. A 203 inches long Kaplan hydro turbine runner shaft was refurbished for a power utility company in the Pacific Northwest. The project included thorough shaft inspections, non-destructive testing, (MT), and the removal of old shaft sleeves. Custom tooling and precision machining were used to restore the shaft to optimal performance. The comprehensive refurbishing process ensured the shaft met the highest quality standards, contributing to the continued efficiency of the hydro turbine. The HESAP cyclopalloid gear machining technology is a highly advanced solution for manufacturing high-precision gears. This innovative process is specifically tailored for cyclopalloid gearing, offering exceptional accuracy and reliability. The technology is widely used for producing spiral bevel gears, which are integral in various industries such as automotive, aerospace, and heavy machinery. HESAP's machines leverage state-of-the-art cutting tools and software to ensure optimal tooth geometry and surface finish. Key features include high-speed spindles, multi-axis control, and automated tool changes, which enhance productivity and reduce cycle times. The process accommodates complex geometries and diverse material types, making it versatile and efficient. Investment casting process. Process begins with the creation of wax patterns, which serve as disposable replicas of the final component. These patterns are made by injecting molten pattern wax into metal dies. After the wax solidifies, the die is opened and the wax pattern is removed. For high-volume production, multi-cavity tools are used to increase efficiency and reduce costs. Complex internal details in the casting can be achieved using soluble wax or ceramic cores. For low-volume production or prototyping, 3D printed patterns using stereolithography from CAD data can substitute traditional tooling. Once the wax patterns are ready, they are assembled onto a wax feed system, known as a sprue. The sprue is designed to provide a pathway for molten metal to flow into the mold during casting, ensuring sound, defect-free components. Assembled wax patterns and sprues, referred to as trees, are coated in a ceramic shell. This involves repeatedly dipping the assembly into a ceramic slurry, followed by drying, to build a robust mold with a thickness of 3/8 to 1/2 inch. The initial ceramic coat, or primary coat, is applied under controlled conditions to ensure detail accuracy, while subsequent layers add strength. Wax is then removed by heating the ceramic shell in an autoclave or furnace, leaving a hollow mold. The molds are preheated to about 1,700 degrees Fahrenheit to prepare them for the thermal stress of molten metal. The molten metal is poured into the preheated molds, filling the cavities and capturing the intricate details of the original wax patterns. After cooling, the ceramic shell is removed through blasting, vibration, or chemical methods. The castings are separated from the sprue, cleaned, and undergo any required finishing processes, such as heat treatment, non-destructive testing, machining, or plating. The drop forging process is a specific type of forging where a hammer or press is used to shape metal into a desired form by striking a heated billet. This process is particularly effective for creating parts with complex shapes, such as automotive components, aerospace parts, and industrial machinery. The drop forging process typically involves placing a heated metal billet between two dies, which are then brought together by the hammer's impact. The die's shape determines the final shape of the forged component. In modern drop forging operations, hammers are generally classified into two types: gravity hammers and power hammers. Gravity hammers rely on the force of gravity to drive the hammerhead, while power hammers use a motor to generate force, allowing for higher impact energy and greater control over the process. These hammers are capable of producing a wide range of parts, from simple to highly intricate geometries, with exceptional precision and surface finish. The advantages of drop forging include not only the strength of the forged parts but also the efficiency of the process. Drop forging is highly efficient for producing large quantities of parts in a relatively short amount of time. The process also produces minimal waste compared to other metalworking techniques, as the material is only deformed and not cut away. This makes it an environmentally friendly manufacturing option, especially when producing parts from high-cost materials such as titanium and specialized alloys. Here's an overview. The process begins by securing the raw material, 2.5-inch diameter 6061 T6 aluminum bar stock, in the 10-inch 3-jaw chuck of the main spindle. The LNS quick load bar feeder supplies the stock, ensuring smooth operation and material continuity. With the main spindle spinning at up to 4,000 revolutions per minute, the rough turning phase shapes the rook's general profile. Using a cutting speed of 450 surface feet per minute for dry cuts, the lathe efficiently removes excess material. Once the rough shape is complete, the turret, equipped with a variety of tooling, performs detailed cuts. The C-axis control allows precise angular positioning, enabling features like the rook's crown to be created accurately. The Y-axis adds versatility for off-center operations, essential for intricate grooves and patterns. The turret's milling power, 5.5 kilowatts at 6,000 revolutions per minute, is used to machine the rook's intricate top details, such as the castle-like crenellations. The 0.001 degrees Celsius axis resolution ensures precision during this phase. The part is handed off to the 6-inch sub-spindle for operations on the opposite end, such as finishing the base. This is powered by an 11 kilowatts motor, enabling powerful yet precise machining. The parts catcher collects the finished rook, ensuring no manual handling errors. The rook undergoes dimensional checks using the integrated tool setter and coolant flush for a polished surface. The Mori Seiki NL2500 CNC's high-speed, multi-axis design ensures efficiency and precision in crafting a flawless chess rook. The Index MS40 multi-spindle CNC machine is a versatile, high-productivity solution for machining bars and chucked parts. Its modular design supports a variety of configurations, enabling customization to meet diverse manufacturing needs. Equipped with up to 12 CNC cross slides, Y-axes, and synchronous spindles, the MS40 delivers dynamic and efficient machining operations. The machine's V-shaped tool carrier arrangement at every spindle position ensures optimal flexibility, allowing external and internal machining with both fixed and driven tools. This design enables complete machining processes at each station, eliminating the need for secondary operations. The MS-40 also offers the unique ability to operate as a twin 3-spindle machine, enhancing its efficiency and throughput. Key features include high-speed synchronous spindles equipped with C-axis capabilities for precision-driven operations. For backworking, the machine can accommodate up to 6 tools per synchronous spindle, or a maximum of 12 tools with 2 synchronous spindles. These configurations support comprehensive machining solutions in a single setup, improving productivity and reducing cycle times. Efficiency and automation in modern drop forging. Modern advancements in automation and computer numerical control (CNC) systems have significantly improved the drop forging process. Today's forging hammers are integrated with automation technologies that enhance the precision and repeatability of each forging cycle. These advancements also allow for the use of closed die forging, where the billet is placed in a die cavity that is precisely matched to the final component shape. This method minimizes material waste and improves the consistency of parts. Automation has also streamlined the handling of materials, reducing the need for manual labor and increasing throughput. Computer-aided design (CAD) and computer-aided manufacturing (CAM) systems play a critical role in the design of the dies and in optimizing the forging process. With these technologies, manufacturers can predict the behavior of the material during the forging cycle, ensuring that the final part will meet the required specifications. Furthermore, the use of heat treatment processes after drop forging helps to further enhance the mechanical properties of the components, such as tensile strength and resistance to wear. The ability to control the temperature during the forging process, followed by controlled cooling, ensures that the final product exhibits the desired physical properties. Applications of modern forging technology. Modern forging technology, particularly drop forging, is widely used to produce components that are subjected to high stress and harsh environments. A forging hammer is a crucial tool in modern forging technology. It works by applying high-impact energy to a heated metal billet to shape it into the desired form. This is typically achieved through repeated blows delivered by a hammer that moves up and down, forcing the metal into a die. The hammer's force can range from 1 ton to over 10 tons, depending on the requirements of the forging process. Modern forging hammers are equipped with advanced control systems that ensure precision, speed, and consistency in every strike. This precision is essential for manufacturing parts that require exact tolerances, such as engine components, gears, and turbine blades. One of the key advantages of using a forging hammer is its versatility. It can be used for a variety of metals, including steel, aluminum, and titanium, making it suitable for diverse industries. The energy delivered by the hammer is particularly useful for producing components that need to be highly resistant to stress and fatigue. These components are often subjected to extreme conditions in their end-use applications, such as high temperatures and heavy loads, where their performance is critical. The process begins with the upsetting of the starting stock, where the metal is compressed to increase its diameter. This step refines the grain structure and prepares the material for subsequent operations. The punching phase creates a central hole in the workpiece, forming the initial ring shape. The punched preform is then subjected to rolling between a driver roll and an idle roll. This controlled deformation expands the ring's diameter while reducing its wall thickness, ensuring uniformity and structural integrity. Ring rolling. Ring rolling is a specialized forging process designed for creating seamless rings with superior strength and precision. The process begins with a circular preform, which is pierced and then rolled between two rolls, a driver roll and an idle roll, to expand the ring radially while reducing its wall thickness. Open die forging. In open die forging, the metal is shaped by compressive forces without being fully enclosed by the die, allowing for versatility in part design. A key step in this process is notching, where grooves or cuts are strategically introduced into the workpiece. These notches guide subsequent deformation, making it easier to achieve the desired final shape. Open die forging is ideal for producing large and custom components like shafts, discs, and blocks. It is especially valued for creating parts with exceptional strength, improved grain flow, and resistance to fatigue. Hammer forging. Hammer forging uses a high-speed hammer to deliver repeated blows to a workpiece, gradually shaping it into the desired form. This process is commonly applied in both open die and closed die setups. Progressive forging. Progressive forging involves multiple forming stages, where the material passes through a series of dies to achieve incremental shaping. This process is ideal for producing complex geometries and precise dimensions with high repeatability. Progressive forging into round shapes. The process starts by progressively deforming a bar or billet into a near-round shape through a series of dies. Each stage incrementally improves the dimensions and surface finish, ensuring a uniform final product. Step forging. A variation of progressive forging. Step forging involves successive deformation to create parts with varying cross-sections. This technique is particularly useful for shafts, spindles, and stepped components. Progressive forging of the second half. In some cases, forging is divided into two halves. The first half forms the initial shape, and the second half completes the forging process. This ensures tighter tolerances and improved material distribution, especially for asymmetrical or elongated components. Bar forging. Bar forging refers to the process of forging pre-rolled or pre-cast bars into specific shapes or dimensions. It is a straightforward method that combines cost efficiency with material strength, often used in applications such as axles, levers, and small machine components. Applications and advantages. Forging, in all its forms, offers distinct advantages over other manufacturing processes. These include improved mechanical properties due to refined grain flow, reduced porosity, and the ability to work with high-strength materials. Blasting prepares surfaces with a 3,200 mm wide system achieving Class 2.5 and 3.0 finishes. Next, plate processing handles plates up to 4 meters by 25 meters using advanced techniques like drilling, milling, plasma cutting, and oxy-fuel cutting, resulting in an as-cut plate finish. Plate rolling accommodates varying thicknesses, 100 mm for 4 meters wide plates and 125 mm for 2.8 meters wide plates. Twin tandem sub-arc welding, guided by a weld selection library and laser seam tracking, ensures high-quality, precise welds. Processes like long seam and circular seam back milling further enhance weld fusion while minimizing heat input. Shell growing lines handle components weighing up to 80 t, while nickel-overlaid tube sheets are precisely prepared. "3D robotic cutting enables exact penetrations for dished ends and shells, and robotic GMAW welding maintains as-cut surface finishes. Tube bundles are fabricated using orbital TIG welding, ensuring durability and uniformity. The furnace, 7 meters by 7 meters by 25 meters, supports post-weld heat treatment. After painting with prime and top coats, components undergo secure loading for dispatch. Hydro testing validates structural integrity, concluding the process. These advanced methodologies deliver pressure vessels and heat exchangers that meet the highest industry standards.